Now we're going to be taking a closer look at arithmetic and geometric sequences. So we have two different types of sequences. Arithmetic sequences occur whenever we have a pattern that uses addition or subtraction. So we either add or subtract to get to the next term in the sequence. Geometric sequences have a pattern using multiplication or division. So you must multiply or divide by something in order to get to the next term in your sequence. An arithmetic sequence is a sequence where the difference between consecutive terms stays constant. Now, consecutive means terms one after the other. Now, this difference is called the common difference, and we denote that using a D. So, for example, if I'm looking at this sequence here, I can see that each time I am adding 3. So to get to the next term, I'm adding 3. But I can also say that I take an plus 1 and subtract 3 to get to an. So the common difference there between the terms would still be 3. So D would be 3 for that particular sequence. We have two different types of formulas that can represent an arithmetic sequence. We have our recursive formula, which requires two things, an initial condition and then the recursive formula. So a sub n is dependent on a sub n minus 1 using the common difference. Or you can have it in terms of a sub n plus 1 being dependent on a sub n, also using the common difference. Or we have the explicit formula, which can build the entire sequence, and we use a sub 1 as well as the common difference to build that formula. In a geometric sequence, the ratio of any two terms and its preceding term is a constant value. Now the word ratio, remembers, means to put it in a fraction and to compare the two numbers using division, and preceding means the term right before it. So whenever I take a sub n plus 1 and I divide it by a sub n, I should always get a constant value, r. Now this constant value is our common ratio. I have two different ways to represent my geometric sequence. I can use the recursive formula, which requires two things, initial condition as well as the recursive formula. This recursive formula relates a sub n to a sub n minus 1 using our common ratio, or a sub n plus 1 to a sub n using, again, the common ratio. We also have the explicit formula, which can build the entire sequence, and we only need the first term in the sequence as well as our common ratio to do that. For these examples, we want to identify if we have geometric or arithmetic sequences. If we have a geometric sequence, we want to find the common ratio, r. If it's arithmetic, we want to find our common difference, d. So looking at this first example, we want to see if we are adding or subtracting, or are we multiplying or dividing? So from 3 to 6, 6 to 12, well, from 3 to 6, I could add 3 to get 6. But then if I add 3 again to 6, I should get 9, not 12. So it doesn't look like I'm going up by the same amount using addition. And I'm for sure getting bigger, so I'm not subtracting anything. So let's check to see if this is geometric. So if it's geometric, I can take the ratio of the terms and find the common ratio. So 6 over 3 gives me 2. And then if I do 12 over 6, again I get 2. If I do 24 over 12, again I get 2. And 48 over 24, again I get 2. So it looks like my common ratio is 2, so r is 2. You can also just see that each time we are multiplying by 2. For the second example, 1 to 5, 5 to 9, well, 1 to 5 I would add 4, 5 to 9 I would add 4, 9 to 13 I would add 4. So it looks like each time I'm adding 4. Now we can also look at it as subtracting the consecutive terms. So 5 minus 1 gives me 4. 9 minus 5 again gives me 4. 13 minus 9 gives me 4. So our common difference here is 4. Writing an explicit formula for an arithmetic sequence can be tricky, but the key is to finding the common difference. For this particular sequence, we already found the common difference to be 4, which means each time I'm adding 4 to get the next term. Now, repetitively adding 4 is the same as multiplying a constant times 4, which we can represent by saying 4n. Now, this does not represent our sequence, however, because if I were to find a sub n equals 4n, a sub 1 would be 4 times 1, which is 4. But my a sub 1 is 1. So what do I have to do to this to adjust it to get back so that my a sub 1 is 1? Well, I can subtract 3. If I subtract 3, now we can see a sub 1 would be 4 times 1 minus 3, which is in fact 1. And you can go ahead and double check. A sub 2 would be 4 times 2 minus 3. Well, 8 minus 3 is 5, and my a sub 2 is 5. So my explicit formula for this sequence is a sub n equals 4n minus 3. We can also use this formula to find the explicit formula for an arithmetic sequence. A sub n equals a sub 1 plus n minus 1 times d. So plugging in what we know for this particular sequence, we have a sub n equals a sub 1 here is 1, plus we must keep the n there, minus 1 times our common difference, which we found to be 4. So distributing, a sub n equals 1 plus 4n minus 4. Combining like terms, we get 4n minus 3 equals a sub n, which is what we already previously found. So you can do either method. This first method does not require you to memorize a formula. The second method does. When dealing with an arithmetic sequence, we represent repetitive addition with multiplication. So since you are adding a value each time, we represent that by multiplying to get our explicit formula. Now for a geometric sequence, we are multiplying each time to get to the next term. So 2 times 2 times 2, well, I can represent that as 2 cubed. So we're going to be using exponents to represent our repetitive multiplication in a geometric sequence. So for this particular geometric sequence, we already found r to be 2. Now a sub n is not going to be 2 to the nth power, because if you double check, a sub 1 would be 2 to the first, which would be 2, but my a sub 1 is 3. So I need to adjust this in order to get back to 3 being my first term. So I need to multiply this by something that will get it back to 3. So what can I multiply 2 by to get it back to 3? Well, it's going to have to be a fraction. So if I take 2 and I multiply it by 3/2, well, numerator times numerator, denominator times denominator, I get back to 3. So in order to adjust this, I'm going to say a sub n is going to be 3/2 times 2 to the n power, and that is going to be my explicit formula for this geometric sequence. Now you can double check. If I have a sub 2, well, that's 3/2 times 2 to the second power, which is 3/2 times 4, which is 12 over 2, which is indeed 6, and a sub 2 is 6. We can also use the formula a sub n is equal to a sub 1 times r to the n minus 1 power. Now using this formula, plugging in what we already know, a sub n equals, a sub 1 we have is equal to 3, r we found to be 2. So we have a sub n equals 3 times 2 to the n minus 1. Now using our exponent properties, I can rewrite this as a sub n equals 3 times 2 to the n times 2 to the negative first power. Now 2 to the negative first power is the same as saying 1 over 2. Now combining our like terms of 3 and 1/2, we get 3/2 times 2 to the n power equals a sub n, which we know is what we already found to be our explicit formula. So I am absolutely fine with you leaving it in this form, but that requires you to memorize this formula here. But if you do it the first way, you do not need to memorize anything. You just need to do some adjustments to get back to a sub 1. Because we have two different types of sequences, we're going to have two different types of means. So anytime you're missing a middle term between two terms, depending on the type of sequence, we can use the arithmetic or geometric mean to find that missing term. So for an arithmetic sequence, we're going to use the arithmetic mean, which is what you normally think of whenever you find the mean. So we're going to add the two outside values and then divide by 2 to find the missing term. So 74 divided by 2 gives me 37. So our missing middle term here will be 37. To check our work, you can see that the common difference will stay constant between the terms. Now for a geometric sequence, we have to do it a little bit differently. So remember, our geometric sequence is defined by having a common ratio. The common ratio is found by taking the term after and dividing it by the term before to find the constant common ratio. So if I want to find the middle term a, well, a over 48 needs to be equal to the term after it divided by a. Cross multiplying, a squared is equal to 144. Taking the square root, a can be positive or negative 12. So we have two possibilities here, depending on the sign of our common ratio. And you can check again, 12 over 48 is going to be equal to 3 over 12, which is 1/4. Or checking the negative version, negative 12 over 48 will be equal to 3 over negative 12, and then your common ratio would be negative 1/4. Now a shortcut way, instead of doing the proportion and cross multiplying, is just multiplying the two outside terms and then taking the square root. Alright guys, now I want you to try these 3 example problems. You can use the notes as well as your reference sheet.